So today let's discuss the remaining questions of real analysis. There were only 2 to 3 topics left in real analysis. One is uniform continuity, one is differentiation and integration under integration sign, and there's one more topic that includes basically miscellaneous questions that were asked on real analysis. So we'll start with differentiation under integration sign, and in the next video we'll look after the uniform convergence questions that were asked. So firstly, differentiation under integration sign, majority of the questions can be dealt using the Leibnitz rule that is there. So let me just state the Leibnitz rule first and then we'll move on to discuss the questions. So basically Leibnitz rule is applicable on a function which is basically a two variable function. Let f be a function in xt, and suppose we want to integrate this, let's say ax bx, and we are integrating it with respect to x. And since f is a function dependent on two variables, so often the calculation gets too complicated. So in order to simplify it, we basically use Leibniz rule. So the Leibniz rule states that if, let's say, I want to differentiate it with respect to t, and here limits are also dependent on, let's say, x comma t, ax comma t, and likewise here we have bx comma t. So if I to do this differentiation, so by Leibniz rule it is equals to integration ax comma t bx comma t del by del t fxt dx plus f of x comma bx and differentiation of this with respect to t del by del x bx comma t, likewise minus f of x comma ax comma t times del by del x ax comma t. So first basically we differentiate the integrand that is there, and then we move on to basically differentiate the limits that are there. Here it is, I guess, bx only. So that's the general Leibniz rule. Now let's see how we can use it in different questions that were asked. So the question 1 is, we are supposed to evaluate this integration, that is, let's name it as I for time being. Integration from 0 to infinity tan inverse ax divided by x times 1 plus x square dx. Now if you see that it is dependent on basically two things. One is a and x. So let's just differentiate it with respect to a. So if I calculate d by dA, integration from 0 to infinity tan inverse ax divided by x times 1 plus x square dx, so it will be equals to, first I'll differentiate the integrand that is there, so that will give me integration from 0 to infinity 1 by x times 1 plus x square times d by dA tan inverse ax. I'm able to do so because x, we are differentiating it with respect to a, so x 1 by x into 1 plus x square will act as constant, so plus, and since if you observe that the upper limit and lower limit are constant and differentiation of constant is 0 basically, so the other two terms will reduce to 0. So the two terms states that x times 1 plus x square tan inverse infinity times x and differentiation of infinity, which will be 0 minus tan inverse 0 times x divided by x times 1 plus x square times differentiation of 0 with respect to a. So these two terms will reduce to 0 because we have a differentiation of infinity and 0 as 0. So these two terms will reduce to 0. So I'll be left with integration 0 to infinity 1 divided by x times 1 plus x square, and if I differentiate this, basically tan inverse ax with respect to a, it will give me 1 divided by 1 plus a square x square, and differentiation of ax will give me x dx. Now this x balances out this one, so it will be equals to integration from 0 to infinity 1 divided by 1 plus x square times 1 plus a square x square dx. Now if you see that the calculation has become has been simplified, we can easily integrate this term with the help of partial fraction. So if we use partial fraction to break this term, so it will be equals to 0 to infinity 1 divided by 1 plus x square minus 1 plus a square x square. So it will be 1 plus a square x square minus a square minus a square x square, and I need to divide by 1 divided by 1 minus a square, I guess. Let me check it once. So it will be 1 plus a square x square minus a square x square. And yeah, so this is the partial fraction of this term, and we can easily now integrate them separately. So it will be equals to 1 divided by 1 minus a square tan inverse x 0 to infinity minus tan inverse ax, or I can, the second term I can write it as minus integration 0 to infinity dx divided by 1 by a square plus x square. So this will be equals to 1 divided by 1 minus a square tan inverse infinity minus tan inverse 0 minus 0 to infinity dx divided by 1 by a square plus x square. And this simplifies to tan inverse infinity basically pi by 2, and tan inverse 0 is 0. So it will be 1 minus a square pi by 2 minus, this simplifies to tan inverse ax divided by constant, and here constant term is basically 1 by a. So it will be 1 divided by 1 by a, that is a only, and limit from 0 to infinity. So if I plug in the limits, it will be 1 minus a square pi by 2 minus a times pi by 2, and this simplifies to, I can pull out pi by 2 outside, so it will be pi by 2 times 1 minus a divided by, I can write 1 minus a square as 1 minus a times 1 plus a, and this balances out this one, so it will be pi by 2 times 1 plus a. Now if you observe that we got pi by 2 times 1 plus a as value of the differentiation of this integral, but we are supposed to solve this. So what we'll do is we'll again integrate it with respect to a basically to get the required value. So if I do so, my I will be equals to integration pi by 2 times 1 plus a dA, which will be equals to pi by 2 log 1 plus a, and that's the final answer basically. That's the thing that we'll get after integrating the given term. This is what we'll get after integrating. This is the final answer. Now let's move on to discuss the next question. Now the second question is also basically based on the differentiation under integration sign. So we'll be using Leibnitz Rule. So let's name the integration as I. So that is 0 to pi log 1 plus cos alpha sin x divided by sin x dx. So if you see that the integration is based on both alpha and x, so what we'll do is we'll just differentiate it first with respect to alpha. So di by d alpha will be equals to d by d alpha integration from 0 to pi log 1 plus cos alpha sin x divided by sin x dx. So if I differentiate it, it will be equals to, using Leibniz rule, 0 to pi d by del alpha log 1 plus cos alpha sin x divided by sin x dx plus, if let's just name the integrand as, let's say, fx comma alpha. So the next term will be, we need to plug in the values of x, so it will be f pi comma alpha and differentiation of pi with respect to alpha minus f0 comma alpha and differentiation of 0 with respect to alpha. Now since pi and 0 are constant, so their differentiation with respect to alpha will be 0. So this term reduces to 0 and this also turns to 0. So it will be equals to integration from 0 to pi del by del alpha log 1 plus cos alpha sin x divided by sin x dx. Now if I differentiate it, it will be equals to integration from 0 to pi. I can pull out 1 by sin x because that's constant since we are differentiating it with respect to alpha. So it will be 1 divided by 1 plus cos alpha sin x. Now if I differentiate it, differentiation of cos alpha will be minus of sin alpha, and since sin x will act as constant, so it will be equals to this. Now I can balance out this sin x with this one, so I'll be left with integration from 0 to pi minus sin alpha divided by 1 plus cos alpha sin x dx. Now this sin alpha will act as constant since we are integrating it with respect to x, so I can pull out minus sin alpha outside, so 0 to pi, and I can substitute sin x as 2 tan x by 2 divided by 1 plus tan square x by 2. So it simplifies to dx divided by 1 plus cos alpha times 2 tan x by 2 divided by 1 plus tan square x by 2. Now if I simplify it, it will be equals to minus sin alpha times 0 to pi 1 plus tan square x by 2 divided by 1 plus tan square x by 2 plus 2 tan x by 2 times cos alpha dx. Now what I can do is I can assume 10, since if you observe that it is basically in the denominator we have quadratic equation in tan square x by 2, so I can assume tan x by 2 as some u, so it will basically reduce to sec square x by 2 times 1 by 2 dx equals to du. And if we see the change in limit, so as when x is equals to pi, so u will be equals to infinity, basically u approaches infinity, and when x is equals to 0, u is approaching to 0, so the given integration reduces to minus sin alpha integration from 0 to infinity. And if you observe that this 1 plus tan square x is basically sec square x, because we have a formula that is 1 plus tan square x equals to sec square x, so the integration reduces to, this will be basically sec square x by 2 dx, and using this relation we can replace it with 2 du, so it will be equals to 2 du divided by 1 plus u square plus 2u cos alpha. Now we can easily form whole square in the denominator in order to solve it, so it will be minus sin alpha 0 to infinity 2 du divided by u square plus 2u cos u, sorry, it's 2u cos alpha plus cos square alpha plus 1 minus cos square alpha. So what I did is I just added and subtracted cos square alpha in denominator in order to form a complete square, so it will be equals to minus sin u integration from 0 to infinity 2 times du divided by u plus cos alpha square, u square plus cos plus 1 minus cos square alpha will be equals to sin square alpha. Now if I integrate it, it will basically be equals to minus, it is sin alpha, minus sin alpha into tan inverse u plus cos alpha divided by sin alpha, and in limit varies from 0 to infinity, and divided by sin alpha, because this is because integration of 1 divided by 1 a square plus x square dx is equals to 1 by a tan inverse x by a. So using this result we got this. Now if we just plug in the limits, it will be equals to minus tan inverse infinity minus tan inverse cos alpha divided by sin alpha. So it will be equals to minus of pi by 2 minus tan inverse cos alpha by sin alpha will be cot alpha, and this simplifies to minus pi by 2 plus tan inverse pi by 2 minus yes, it will be basically equals to pi by 2 minus tan inverse tan alpha, and we have 2 as well here, this 2, so it is 2 and it will be minus pi plus pi minus 2 tan inverse alpha, that will be equals to minus of 2 alpha. Now so what I got is di by d alpha as minus of 2 alpha. So from here, if we need to evaluate value of I, so I need to integrate it with respect to alpha. So my alpha will be basically equals to, I will be basically equals to minus of alpha square plus c. Now we need to evaluate this constant c as well, but if you observe, initially my I alpha was basically my I alpha was equals to integration from 0 to pi log 1 plus cos alpha sin x dx divided by sin x. Now if I calculate, like if from here I evaluate value of, let's say I pi by 2, so it will be equals to integration from 0 to pi by 2 log 1 plus cos pi by 2 sin x dx divided by sin x, and we know that cos pi by 2 is 0, so in the numerator we will be left with log 1 divided by sin x, and log 1 is also 0, so I pi by 2 is 0. Now we can use this information, that is I pi by 2 equals to 0 here. So if I evaluate I pi by 2, it will be equals to 0 minus pi by 2 square plus c. So from here I got my c as pi by 2 square. So this basically gives me I as minus alpha square plus pi square by 4. So that simplifies to pi square minus 4 alpha square divided by 4. So I got my value of I as this, and that's what we are supposed to show in the question. So this completes our second question. So let's move on to discuss the third question. So the third question asks us that we are supposed to show that x raised alpha divided by log x dx is equals to log 1 plus alpha. Again we'll restore to using the Leibnitz rule. So if let's name it as I of alpha as integration from 0 to 1 x raised alpha minus 1 divided by log x dx. Now if I differentiate it with respect to alpha, so it will be equals to d by d alpha integration from 0 to 1 x raised alpha minus 1 divided by log x dx. So this will be equals to integration from 0 to 1 d by d alpha x raised alpha minus 1 divided by log x dx plus, if we let's name the integrand as fx comma alpha as x raised alpha minus 1 divided by log x. So f1 comma alpha and differentiation of 1 with respect to alpha minus f0 comma alpha and differentiation of 0 with respect to alpha. Now since 1 and 0 are constants, so their differentiation with respect to alpha will be 0. So this term becomes 0 and this term also becomes 0. So it will be equals to integration from 0 to 1 d by d alpha x raised alpha minus 1 divided by log x dx. Now if we differentiate the integrand with respect to alpha, now observe that 1 by log x is constant, so we can easily pull out. This is constant with respect to alpha, so because of that only we are able to pull this out. So it will be equals to 1 by log x and d by d alpha x raised alpha minus 1 dx, and it simplifies to 0 to 1 by log x, and differentiation of x raised alpha with respect to alpha will be x raised alpha and log x, and differentiation of 1 will be 0. So we have dx here. So this log x balances this one, so we'll be left with integration from 0 to 1 x raised alpha dx. Now its integration will be, integration with respect to x will be x raised alpha plus 1 divided by alpha plus 1, and limit varies from 0 to 1. So this simplifies to 1 divided by alpha plus 1 minus 0 divided by alpha plus 1, so that reduces to 1 divided by alpha plus 1. So this is the value of di by d alpha. Now we need to evaluate the value of I, so we need to integrate it with respect to alpha, so that will be equals to d alpha divided by 1 plus alpha, which will be equals to log of 1 plus alpha plus c. Now we need to find this constant c as well in order to get the value of exact value of I. Now if you observe that the initial integration that we have is I alpha was equals to integration from 0 to 1 x raised alpha minus 1 divided by log x dx. I guess that's the one we have. Okay. Now if we evaluate I of 0, so it will be equals to integration from 0 to 1 x raised 0 minus 1 divided by log x dx. X raised 0 will be 1 and 1 minus 1 0, so this is 0. We got I of 0 as 0. Now we can use it here. So I of 0 will be equals to log 1 plus 0 plus c, and so from here we get 0 equals to c. So our I of alpha will be equals to log 1 plus alpha, and that's exactly what we were supposed to show. We are supposed to show that this integration, which we assumed as I alpha, is equals to 1 plus alpha. So this completes our question. Now we'll move on to discuss the next question. So this question says that we are supposed to evaluate this integration, that is from 0 to pi by 2 log of alpha square cos square theta plus beta square sin square theta d theta. Now if you observe that it is a function in alpha, like the integrand is basically a function in alpha, theta and beta. So first we need to reduce it to basically two variables. So let's see how we can do that. So we are supposed to evaluate 0 to pi by 2 log alpha square cos square theta plus beta square sin square theta d theta. This is what we are basically supposed to evaluate. So first thing is, let's just replace cos square theta with 1 minus sin square theta. So it will be 0 to pi by 2 log alpha square cos square theta will be 1 minus sin square theta plus beta square sin square theta d theta, and that simplifies to integration from 0 to pi by 2 log alpha square plus beta square minus alpha square sin square theta d theta, and I can further simplify it to integration from 0 to pi by 2 log alpha square times 1 minus alpha square minus beta square divided by alpha square sine square theta d theta, which is equals to integration from 0 to pi by 2 log alpha square plus log 1 minus alpha square minus beta square divided by alpha square sine square theta d theta. Now what I can do is I can write it as, since log alpha square with respect to theta will be constant, so I can pull it out. So it will be log alpha square integration from 0 to pi by 2 d theta plus integration from 0 to pi by 2 log 1 minus, let's rename it, let's write it as 1 minus c square sine square theta d theta. So what I have done is I have assumed c square as alpha square minus beta square by alpha square. Now this term will be log of alpha square times pi by 2 plus, let's name it as this integration as I1. So now we are supposed to evaluate I1. So I1 is equals to integration from 0 to pi by 2 log 1 minus c square sine square theta d theta. Now we are supposed to evaluate it. Now we'll basically use Leibnitz rule here in order to evaluate this integration. So let's just differentiate it with respect to c. So di1 by dc will be equals to integration from 0 to pi by 2 d by dc, basically del by del c log 1 minus c square sine square theta d theta plus, if this integration is basically, let's assume it as f theta comma c, so it will be f pi by 2 comma c and differentiation of pi by 2 with respect to c minus f 0 comma c and differentiation of 0 with respect to c. Now since pi by 2 and 0 are basically constant, so these two terms will basically reduce to 0. So di1 by dc will be equals to integration from 0 to pi by 2, and if we differentiate it with respect to c, I'll get 1 minus c square sine square theta minus 2c sine square theta d theta. So, and if I further simplify it, it will be 2 by c integration from 0 to pi by 2 minus c square sine square theta divided by 1 minus c square sine square theta d theta, and it further simplifies to, I can just add and subtract 1 in order to simplify it. So it will be 2 by c integration from 0 to pi by 2 1 minus c square sine square theta minus 1 divided by 1 minus c square sine square theta d theta, which will be equals to 2 by c integration from 0 to pi by 2 1 minus 1 divided by 1 minus c square sine square theta d theta, and it will be equals to 2 by c times pi by 2 minus 2 by c integration from 0 to pi by 2 d theta divided by 1 minus c square sine square theta. So let us put cot theta equals to t, and it simplifies to cos x square theta d theta equals to dt. It will be minus cos x square theta d theta. So let's see how it further simplifies. So it will be equals to, basically di1 by dc will be equals to pi by c minus 2 by c integration from, and change in limit will be as theta is 0 when theta equals to 0, t approaches infinity, and when theta equals to pi by 2, t approaches 0. So it will be 0 to infinity. D theta will be d divided by minus 1 plus t square divided by 1 minus c square times 1 divided by 1 plus t square, because since cot theta equals to t, so from here cot square theta equals to t square. So, and we know that cot square theta is basically cosec square theta minus 1 equals to 2t square. So from here cosec square theta will be equals to 1 plus t square, and we know that cosec theta is basically 1 by sine theta. So from here sine square theta will be equals to 1 divided by 1 plus t square. So it reduces to pi by c plus 2y, or let's keep it as minus only, minus 2 by c integration from 0 to infinity dt divided by 1 plus t square minus c square, which will be equals to pi by c minus 2 by c integration from 0 to infinity dt divided by 1 minus c square plus t square, which will be equals to pi by c minus 2 by c 1 by square root 1 minus c square tan inverse t divided by square root of 1 minus c square 0 to infinity, which will be equals to pi by c minus 2 by c square root 1 by c square tan inverse infinity minus tan inverse 0 divided by, yeah, that's all only, because 1 by c square is constant. So it will be equals to pi by c minus 2 by c square root 1 minus c square. Tan inverse infinity will be pi by 2 minus tan inverse 0 is 0, and this 2 balances this one. So it will be equals to pi by c into 1 minus 1 divided by square root of 1 minus c square. So from here what I got is di1 by dc equals to pi by c minus pi by c square root 1 minus c square, but we are supposed to evaluate value of I1. So I1 will be integration of this with respect to c. So it will be pi by c divided by pi by c square root 1 minus c square dc, and if we evaluate it, it will be equals to pi times, it will be basically equals to pi times log c minus pi times log 1 minus square root 1 minus c square divided by c plus a. So we got I1c as this, but we know that our I11 was basically equals to this. So if we evaluate I10, so from here, like from this equation, if I calculate I1 of 0, so it will be equals to 0 to pi by 2 log 1 minus, since I plugged in 0 as 0, so it will be log 1 only, that is 0. So it will be equals to 0 only. So I10 is 0. Now from here also, if I so if I simplify it, it will be equals to pi log c square divided by 1 minus square root of 1 minus c square plus a. Is that it? Log c divided by, and that simplifies to pi of log, we are just rationalizing it, it will be c square divided by 1 minus 1 plus c square times 1 plus square root of 1 minus c square plus a. and this balances each other. So it will be equals to pi times log 1 plus square root 1 minus c square plus a, and we have evaluated that I1 at c equals to 0 is 0. So from here 0 equals to pi log 1 plus 1 plus a. So from here we get our a as minus pi log 2. So our I1 will be basically equals to pi log 1 plus square root of 1 minus c square minus pi log 2. This is our I1, but our actual integration value is basically I1 plus log alpha square times pi by 2. So that will be equals to log alpha square times pi by 2 plus pi log 1 plus square root of 1 minus c square minus pi log 2. This is the actual value of integration that we were supposed to evaluate. That is this one. We can further plug in the value of c square that we assumed as alpha square minus beta square divided by alpha square. That will further simplify it. Or you can write it as where c square is basically alpha square minus beta square divided by alpha square. This completes our question. Now let's move on to discuss the next question. Basically this completes our questions on integration under differentiation under integration side. Rest were the practice problems that were there. So only these many questions were asked on differentiation under integration side. So thank you for watching, and please do like, share and subscribe to the channel.